In the beginning, there was a bit. All things originate from information, specifically from its smallest units, bits. The apple is a prime example. Initially, the apple represents the fruit of knowledge, the deadly taste of which brought death and all our suffering to earth. As described in John Milton's Paradise Lost, it embodies information about good and evil. Later, the falling apple's path inspired Newton's universal laws of gravitation. The apple's curved surface metaphorically illustrates Einstein's curved space-time. The genetic code within apple seeds programs the structure of future apple trees. Additionally, the apple stores energy-rich bits in the form of calories, fueling our bodies. Although it appears that an apple contains an infinite number of bits, quantum mechanics laws limit the number of bits. Each atom and nucleus spin holds a few bits. Consequently, the bits in an apple only exceed the number of atoms by a small factor. A bit can exist in two states, 0 or 1. The greater the number of states a system has, the more bits it contains. All physical systems, constrained by energy space, possess a finite number of states and information bits. However, not all bits are equally important. Some bits convey significant information, while others represent random data. The importance of a bit is context-dependent. For instance, the bits coding an apple's DNA are crucial for future generations, whereas bits representing an atom's thermal fluctuation are less important. Yet, there's no definitive mathematical method to assess a bit's significance. The significance varies based on information processing. An electron state transition alters a bit's significance. System dynamics resemble a computation where bits function as instructions. A bit's significance is determined by its impact on other bits in the universe's evolution. This video narrates the story of the universe and the individual bit. The universe is the largest known entity, and a bit is the smallest piece of information. The universe is made up of bits. Every molecule, atom, and elementary particle contains bits of information. In any interaction between these particles of the universe, information is processed by changing these bits. In other words, the universe computes, but it is governed by the laws of quantum mechanics. Therefore, it computes in a way that is intrinsic to quantum mechanics. Its bits are quantum bits. In fact, the history of the universe is a huge constant quantum computation. The universe is a quantum computing machine. Seth Lloyd. You heard me correctly. The universe is a quantum computer. This is the main idea of the book, Programming the Universe, by physicist and Massachusetts Institute of Technology, Professor Seth Lloyd. This video draws inspiration from that book. Seth Lloyd, the author of over 250 scientific papers, has an unparalleled understanding of his research area. Lloyd was a postdoctoral fellow at the California Institute of Technology's Department of High Energy Physics, where he collaborated with Nobel laureate Murray Gell-Mann. He made significant contributions to quantum computing, including proposing the first technological design for a quantum computer. Lloyd demonstrated the feasibility of quantum analog computing by proving Shannon's theorem and developed new methods for quantum error correction and noise reduction. In his book, Programming the Universe, Lloyd asserts that the universe itself is a massive quantum computer, creating everything we observe, including ourselves. According to Lloyd, the universe functions like a gigantic cosmic program. He believes that once we fully understand the laws of physics, we will be able to utilize quantum computing on smaller scales to comprehend the universe entirely. Lloyd calculated that based on the growth of computing power, following Moore's law, in 600 years, we will be capable of fully simulating the universe's behavior. Let's go back to his previous quote. The history of the universe is a vast constant quantum computation. The universe is a quantum computing machine. Many of you might wonder, what exactly is the universe computing? The answer is itself, its own behavior. As soon as the universe came into existence, it immediately began to compute. At first, the constructs it created were simple. They involved elementary particles and established the fundamental laws of physics. Over time, as it processed more and more information, the universe gave rise to increasingly intricate and complex objects, including galaxies, stars, and planets. Seth Lloyd. Life, language, people, society, and culture all exist because matter and energy naturally process information. The universe's ability to compute information explains one of nature's biggest mysteries: how complex systems, such as life, arise from very simple physical laws. Physical laws allow us to predict the future, but only as probabilities. The quantum nature of computation in the universe means that the exact details of future events are always uncertain. Calculating them would require a computer the size of the universe itself. Thus, the only way to know what the future holds is to wait and see. In 1993, I figured out how to build a quantum computer. Quantum computers are devices that utilize the ability of individual atoms, photons, and other elementary particles to process information. They compute in ways that classical computers such as Macs or PCs cannot. As I studied how to make atoms and molecules, the smallest particles in the universe, compute, I became increasingly aware of the natural information processing ability inherent in the universe itself. The complex world we see around us is a manifestation of the quantum computation of the universe. Seth Lloyd. The digital revolution we are experiencing is the latest in a series of information processing revolutions. These include the birth of human languages, the advent of sexual reproduction, the emergence of life, and the very beginning of the universe itself. Each revolution laid the groundwork for the next, enabled by the universe's inherent ability to process data since the Big Bang. A calculating universe creates complexity out of necessity. Life, sex, brains, and human civilization did not arise by chance. Let's explore how the universe processes information and how it relates to us. Starting with quantum mechanics. Quantum mechanics is famous for its paradoxes, which continue to puzzle even the brightest minds. Waves behave like particles, and particles like waves, sometimes existing in two places simultaneously. These paradoxes confuse even Nobel laureates. Quantum computers are based on these unusual properties of the microcosm. An ordinary computer bit is straightforward, either 0 or 1, with no in-between. A quantum bit, or qubit, can be 0 and 1 simultaneously. While a regular computer processes options sequentially, a quantum computer can calculate millions of combinations simultaneously. How does it do this? It operates with the smallest particles of matter, such as atoms, electrons, and photons. Each particle acts as a real information unit, performing logical operations. This is akin to a secret cipher of the universe. Scientists have proven that this principle works in any physical system. Understanding the universe's language involves comprehending how its smallest elements store and process information. This is precisely what scientists designing quantum computers aim to do. The first ideas appeared in the 1980s, but practical realization only became apparent in the 1990s. Since then, numerous engineers have dedicated themselves to developing advanced quantum systems. There are compelling reasons for this. First, modern technology now allows manipulation of matter at such a subtle level. Secondly, traditional electronics is nearing its limits, with transistors soon reaching the size of an atom, making further miniaturization impossible. Third, quantum computers help us understand how the universe itself computes and remembers. To unravel the mysteries of the universe, one must learn its language. The universe effortlessly produces structures of unimaginable complexity, including living organisms, intelligence, and civilization, thanks to nature's hidden language. To decode this cosmic code, we need to master its alphabet. The microcosm is full of objects, ready to serve as living memory, communicating through energy, force, and impulse. Speaking of languages, how does any dialogue begin? With the simplest interaction, like atoms. They are malleable, yet sensitive, easily communicable, but hard to hear. With the right approach, they can be coaxed into performing calculations. Throughout history, information revolutions have repeatedly transformed civilization. One such revolution is occurring now with the development of electronics. However, there have been other significant breakthroughs. Consider the invention of zero and the Arabic numeral system, which revolutionized mathematics, making calculations easier and faster. Early counting tools demonstrated technology's power to make abstract concepts tangible. Take the invention of writing a few thousand years ago. Initially, they were just scratches on clay, but these marks made speech visible and tangible, leading to the first books and chronicles. Writing became a catalyst for cultural development. Although the methods of recording information have evolved, from cuneiform to paper, the primary purpose of writing remains the same. The purpose of writing is to preserve words for future generations. About 100,000 years ago, a significant information explosion occurred with the emergence of human speech. Paleontological data indicates that the development of language coincided with rapid growth in the relevant parts of the brain. New neural networks, combined with the evolution of the vocal apparatus, created a unique biological mechanism for universal communication. This mechanism has allowed humanity to flourish and populate the entire planet. Your tongue and vocal folds are essentially Stone Age high-tech tools. Nature spent a lot of time perfecting them for communication. So, don't let your ancestors down. Speak up, make jokes, write comments. The further back in time, the bigger the revolution. The evolution of the brain and nervous system, the emergence of multicellular organisms and new species, and successful mutations are all milestones on the path to improved information processing. But the biggest revolution occurred 1 billion years ago with the emergence of sexual reproduction. At first glance, sex seems like a risky idea because it carries the potential for losing valuable genetic information. Initially, sex might seem like a lottery, as there's no guarantee that valuable genes will be inherited. But why would nature take this risk? In asexual reproduction, such as bacterial budding, the offspring receive an exact copy of the parental genome. Sexual reproduction leads to recombination, mixing the genes of the parents. Even the most successful gene copies are not passed on unchanged, meaning sex prevents success in this sense. However, sexual reproduction is a powerful generator of diversity. Through chromosome combination, even a small population can produce numerous new gene variations. Sexual reproduction promotes genetic variation while preserving individual genes. Consider a bacterium adapted to a cool climate. If sudden warming occurs, its identical offspring would struggle. The only way for a sexless organism to adapt is through random mutations, most of which fail. The law of change or die conflicts with the principle of genome conservation. Sexual reproduction resolves this conflict through gene recombination. Scientists have calculated that even a population of 1,000 people can create a vast variety of offspring. This is evident from a dark chapter in our history. Humanity faced its toughest evolutionary challenge about 70,000 years ago, when our population dwindled to a critical 2,000 individuals due to the catastrophic eruption of the Toba volcano in Indonesia. The eruption covered vast areas with ash, resulting in a multi-year volcanic winter, referred to as the population bottleneck. The catastrophe severely reduced the human gene pool. However, sexual reproduction allowed for rapid growth in genetic diversity. The survivors' gene recombination led to many new variations, restoring genetic diversity within a few thousand years. Sexual reproduction saved us from extinction. A more fundamental revolution was the origin of life on Earth. This occurred about 4 billion years ago. Since then, living organisms have learned to store information in genes, or DNA sequences. Your genome is as unique as your fingerprints, encoded with 6 billion bits of information, equivalent to a 750 megabyte flash drive. It contains all the information needed to create you. Printing your genome would result in a stack of paper, the height of a 20-story building. Each of our cells contains a significant amount of information that organisms pass on to their offspring, along with some genetic changes or misspellings. Think of it as akin to the Bible, which originally consisted of 4 Gospels that told the same events in different ways. This is how Christianity was born. Over time, heresies emerged because the Gospel texts, once written, were repeatedly rewritten by hand in an era of no photographic reproduction. Errors by scribes were common, and each successive scribe could repeat existing errors and introduce new ones, resulting in a broken phone effect where the original message became increasingly distorted. Not surprisingly, all life on Earth, which relies on DNA, processes far more information than all the world's computers combined. But even the origin of life pales before the very first information revolution, the birth of the universe. Every atom and particle in the universe acts like a tiny processor, continuously exchanging data according to the rigid laws of physics. At the quantum level, even the simplest interactions represent information processing. These basic operations serve as the building blocks to create the complexity of our universe. Consider the game of life, a cellular automaton in which a grid of cells, living, white, or dead, black, obey two simple rules, demonstrating the complex patterns that can emerge from basic interactions. If a living cell has 2 or 3 living neighbors, it continues to live. Otherwise, it dies. If a dead cell has exactly 3 living neighbors, it comes back to life. Otherwise, it stays dead. It seems like such a simple concept, just 2 rules. But when the game of life is initiated, we witness cells swirling into complex patterns, forming stable structures, and even replicating themselves. Some configurations even mimic the movements of living creatures. Remarkably, within this game, it's possible to construct a functional computer that performs calculations. Imagine a computing system built from the simplest interactions and basic rules. This mirrors our universe, where every particle collision and chemical reaction is a minuscule data process. Collectively, these interactions create the vast complexity we see, from atoms to stars, from DNA to the human brain. It's truly grandiose. But what's the machine behind the calculations of the Big Bang? To see it in action, you just need to look around. It's tangible. The universe itself serves as the processor for these universal calculations. Our world is essentially composed of energy. There's an old joke about the complexity of this concept. A question on a physics exam: what is energy? After struggling, a student admits, "I'm sorry, professor. I knew, but I forgot." The professor then dramatically declares, "Friends, tragedy. One person in the world knew what energy is, but he forgot." Shifting to the concept of information, it's often easier to measure the amount of information than to define what it is. Similar to energy or money, it's simpler to quantify than to explain. What is a bit? It's a binary choice. 0 or 1, heads or tails, yes or no, true or false. Each bit represents one of 2 possibilities. 2 bits offer 4 alternatives. 3 bits provide 8, and so on. The number of alternatives doubles with each added bit. To calculate the number of alternatives, simply multiply 2 by itself, as many times as there are bits. For example, 10 bits represent 2 to the 10th power, or 1024 alternatives. The binary system's efficiency enables simple digital circuits, which underpin modern computing. Thus, we extensively use information, even without a precise definition. But does information need to have inherent meaning? Meaning varies based on interpretation. Without context, any string of bits is merely a sequence of zeros and ones. The term "yes" only has significance if the question's context is understood. Philosopher Ludwig Wittgenstein introduced language games to illustrate how word meanings depend on their usage context. Take the interaction where a construction worker simply says "stone" and his assistant understands this as a directive to pass a stone. In straightforward scenarios, the meaning is clear. However, as interactions become more complex, understanding becomes challenging due to the ambiguity of human language. Conversely, computer languages are precise. Each command prompts a definite action, making the meaning of a computer program exactly what the computer does with it. Ambiguity is unacceptable to a machine. Unlike human language, the ambiguity of language is a boon for poets, writers, and flirtation lovers. In short, ambiguity is not a bug, but a feature of our speech. Here's the bottom line. Information fundamentally involves making correspondences between systems. Every symbol stands for something else. A pair of fingers can stand for a cow, people, or abstract concepts. Words are incredibly versatile. They range from orange to freedom, limited only by our vocabulary. A sentence composed of these words accomplishes the greatest feat. It conveys thoughts, ideas, anything the mind can think of. However, in order to understand their meaning, interpretation is required. So, what is a computer? In general, it is a machine that processes information. But what was the first computer like? Was it an abacus, Babbage's mechanical device, a logarithmic ruler, or perhaps something biological like DNA or a brain? If computing means processing information, then almost anything can take on that role. For now, let's limit ourselves to machines specifically designed by humans for computing. The earliest computers, like tools, were stones. After all, the Latin calculus translates to pebbles. The ancients did calculations by laying out pebbles. Stonehenge may have been a large stone computer, calculating the relationship between the calendar and the position of the planets. Any technology imposes limits on computing. Stones are sufficient for addition and subtraction, but they can't handle multiplication and division, so large numbers require many stones. After millennia, we moved on to abaki and counting boards, where skillful operators outnumbered trained users of adding machines. Sometimes, machines give birth to ideas, and ideas give birth to machines. From stone to wood, what material will be the next catalyst for information processing? Bone. If you thought manual multiplication could only be done in columns, I have a surprise for you. John Napier revolutionized it in the 17th century. He carved logarithmic divisions into ivory sticks, turning multiplication into addition. By carving ivory sticks, he put special divisions on them. To multiply numbers, it was necessary to move the sticks so that the marks coincided with these numbers. And so the first logarithmic ruler was born. His creation paved the way to Charles Babbage's metal difference engine, created in the 19th century, a mechanical marvel resembling modern computers, equipped with a processor and memory. Babbage's design surpassed the metallurgical precision and alloy strength of his era, but his efforts kick-started the Industrial Revolution. In the 1940s, a race to create electronic computers based on switches began, culminating in Konrad Zus's creation of the first rudimentary computer in 1941. It was replaced in the US and UK by larger machines that took up entire rooms, but were 1,000,000 times less powerful than your modern smartphone. Despite the huge cost, these early computers justified the effort put into their development. In the 1960s, vacuum tubes and relays gave way to transistors, reliable, compact, and economical solid-state switches. Since then, component sizes have halved about every 18 months, doubling the performance of computers. Long live Moore's law. Computers come in many forms. Digital computers apply logic to bits and can be electronic or mechanical. Classical computers adhere to the principles of classical mechanics using tubes or transistors. Analog computers work with continuous signals, mimicking physical systems. Quantum computers, using quantum mechanics, combine digital and analog principles. Essentially, any computer works like a bit processing factory. It takes bits in batches, interprets them, and puts them to work. By building a pipeline of simple operations, complex calculations can be mass-produced, as demonstrated by the logician George Boole in 1854. In his work, An Inquiry into the Laws of Thought, he showed that any logical expression, regardless of its complexity, can be represented using just 4 operations: not, copy, and ignore. Like the nursery rhyme, don't go there, copy this, take this, and this, or pick one. So, computers are huge circuits made up of these elements, which turns your computer or smartphone from mere hardware into the electronic embodiment of Boolean algebra and logical thinking. In computers, bits are stored in capacitors and magnets on hard disks. A capacitor acts like an electronic bucket. Empty means 0, full means 1. Hard disks store bits using tiny magnets. To learn more about how computers work, watch my video, Human Evolution versus Artificial Intelligence. However, the simplicity of bits does not guarantee predictable computer behavior. As mathematician Kurt Gödel has shown, any sufficiently complex logical system contains unprovable statements, analogous to uncomputable quantities in computing, such as the halting problem. It is impossible to determine in advance whether a running program will stop or run indefinitely. This intrinsic unpredictability parallels the concept of free will in humans. We make decisions without knowing their outcomes in advance. Ironically, logical behavior can lead to unpredictability. Reflecting on the works of Aristotle, the Muslim philosopher Averroes came to the conclusion that it is not the soul, but the ability to think that is immortal in humans. Mind is immortal, precisely because it belongs to all thinking beings in the aggregate, not to each individual person. Similarly, computers have the ability to think. As their capabilities expand, their unpredictability approaches that of humans, making them, in a sense, as immortal as we are. Our universe is made up of atoms and elementary particles. Over the last century, astrophysicists have compiled a science-based chronicle of the history of the universe. It began about 14 billion years ago, with the Big Bang. As the universe expanded and cooled, atoms, stars, galaxies, and planets appeared, presenting us with repeated scenarios with different stars. If the universe is truly infinite, then all conceivable scenarios manifest somewhere within it. The history of the universe resembles a cosmic soap opera, replete with endless plot twists. Traditionally, the protagonist of this saga is considered to be energy, which drives physical systems and has the fundamental property of constancy. Energy can manifest itself in various forms: heat, work, electricity, but it never disappears, following the first law of thermodynamics. However, if the universe came from nothing, where did the energy come from? Physicists offer an explanation based on quantum mechanics. Energy arises from quantum fields that permeate the universe like a universal fabric. The interaction of these quantum fields gives rise to elementary particles such as photons, electrons, and quarks. The energy we encounter, such as sunlight and heat, arises from these quantum fields, increasing as the universe expands. Gravity plays a role similar to extracting energy from these fields, balancing positive energy with the negative energy of gravitational attraction. The conventional view of the universe places considerable emphasis on energy, its quantity, distribution, and activity. However, according to Seth Lloyd, information is central to the physical history of the cosmos. While energy drives systems to action, information dictates their behavior. Energy and information are complementary forces. At the atomic level, matter is in perpetual chaotic motion, where energy manifests as heat and information as entropy, a measure of molecular disorder. The second law of thermodynamics states that entropy, which is invisible information, never decreases, far exceeding the visual information we perceive. For example, it takes millions of times more bits to describe the vibrations of atoms on photographic film than a digital photograph. This is discussed in more detail in the video, The Paradox of Information. Unlike entropy, free energy exists in an ordered state, such as the chemical bonds in a sugar molecule, and is readily used to do work, such as muscle contraction. Energy and information interact according to the laws of thermodynamics that govern all processes in the universe. Energy is conserved while information remains constant. Processing information requires energy, and more energy speeds up the rate of processing. All matter consists of energy, and its specific manifestations are dictated by information. Thus, the history of the universe unfolds as a narrative of the interaction of energy and information. Modern astronomical observations give us the opportunity to reconstruct this story from the Big Bang to the present day. Not only do the laws of nature say that the universe can suddenly arise unaided like a proton, but they don't rule out that the Big Bang had no cause at all. None. Stephen Hawking. The universe began less than 14 billion years ago in the form of a giant explosion. But what was there before the Big Bang? Nothing. There was no time or space. Again, it's not that space was empty. It was absent. Time, on the other hand, had a beginning. Seth Lloyd. Many physicists believe that before the Big Bang, there was nothing, neither time nor space. The universe emerged from that nothingness. Just as a positive number starts at zero, the universe was originally very simple, with minimal information and energy. An early state could be described by just a few bits, or even zero if that was the only possibility. As the universe expanded, it was quickly filled with energy drawn from the quantum fabric of space-time. This energy was free, and the universe remained simple and orderly. However, a few moments later, as particles began to vibrate frantically, the simplicity disappeared. It took quintillions of bits of information to describe this chaos. There was an explosion of information. As the universe cooled, particles condensed into more complex structures: protons, nuclei, and atoms. Each new complexity increased entropy at the macro level. However, the universe remained homogeneous and simple. Today's diversity came about through quantum fluctuations and gravity. Tiny random inhomogeneities were amplified by gravity to form galaxies, stars, planets, and black holes. Gravity also provided the free energy necessary for life, such as sunlight. The amplification of tiny differences through chaos underlies the richness of the forms of our world. Every detail has existed through quantum randomness since the beginning of time, including us. Without quantum mechanics, the universe would be dull and empty. We already know that the universe computes by recording and transforming information, turning everything around us into a universal computer. But is our universe technically a universal digital computer? The answer is no. While the idea is attractive and physics supports universal computing, the universe has much more computing power. The key criterion is modeling efficiency. The laws of physics easily model digital computing, but not vice versa. The quantum nature of the universe is beyond the scope of classical computers. To model a speck of dust for a fraction of a second, a computer would need more memory than the atoms in the universe, and more time than the universe exists. So don't try to model a speck of dust. Quantum computers, however, can effectively model any physical system. Their design allows them to accurately reproduce the behavior of the system, making them indistinguishable from the system itself. The universe, being a physical system, can be accurately modeled by a quantum computer of the same size, meaning that its computing power matches that of a universal quantum computer. Observations and measurements in the universe are indistinguishable from observations and measurements in the quantum computer modeling it. Thus, Seth Lloyd believes that the universe is a quantum computer. Everything we see is the result of its quantum computations. Although we do not yet know the details of these computations, the quantum computational nature of the universe perfectly explains its complexity and diversity. Look at the night sky. Its beauty and diversity stem from simple laws. An old explanation proposed by physicist Ludwig Boltzmann suggested that information in the universe arises from a random process, like flipping a coin. This idea led to the famous image of monkeys randomly typing and reproducing all the world's literature. Even Cicero pointed out the extremely low probability of such a scenario. The accidental creation of a short, meaningful text is extremely unlikely. It would take billions of monkeys, billions of years to type the beginning of Hamlet. By the way, there is a website where your computer can take on the role of a monkey, trying to reproduce passages from Shakespeare in random order. The current record is the random generation by virtual monkeys of the first 24 letters of Hamlet, a task that took 3 decillion monkey years to complete. This emphasizes the near impossibility of random order due to the finite size and age of the universe. Moreover, if the universe operated according to the principle of randomness, new discoveries in it would be just as chaotic. But this is not the case. Observations of new galaxies and patterns in nature are evidence of inherent order. Even using all the computational resources of the universe, we would only be able to randomly generate a few lines of Hamlet, suggesting that Boltzmann's view of a random universe is incorrect. Conversely, Cicero's view that only a complex mind can generate complexity is also wrong. Simple computers that perform basic operations can produce complex results if properly programmed. The programs that control these results can be completely random sequences of bits, which opens up the potential for deriving order from chaos. Imagine that instead of typewriters, monkeys type on a computer that interprets their random keystrokes as programming instructions, potentially producing meaningful results. Short, random programs can generate numbers, fractals, physical models, basically anything. In this analogy, quantum fluctuations provide the universe with random bits, like monkeys typing, and the laws of physics function like a computer, converting these bits into instructions that manifest the diverse forms of the universe. From physics arises chemistry, from chemistry arises life, and from life arises literary masterpieces like Shakespeare's Hamlet. This random programming of the universe transforms our world from a chaotic void into a marvel of complexity and meaning. The idea that physical systems process information was first proposed by physicists such as Maxwell, Boltzmann, and Gibbs in the late 19th century. Maxwell illustrated the relationship between entropy and information with his hypothetical demon that could control heat flows. Imagine you have a magical assistant who sits between 2 rooms. He keeps an eye on the gas atoms near the door between the rooms. When he sees a fast, hot atom flying from the cold room, he opens the door and lets it into the hot room. And when he sees a slow, cold atom from the hot room, he lets it into the cold room. So gradually, the hot room gets even hotter and the cold room gets even colder. It turns out that the assistant, as if to force heat to flow from cold to hot, although usually in nature, it is the other way around. However, Maxwell's demon does not actually violate physical laws. It increases the overall entropy of the system by its actions and the information it processes, thereby supporting the second law, albeit in a more subtle form. By the end of the 19th century, Boltzmann, Gibbs, and Planck refined the understanding of entropy by making it proportional to the logarithm of the number of microstates of a system, effectively linking it to the information needed to describe those states. Boltzmann valued this understanding so highly that he willed the entropy formula to be engraved on his tombstone. This early work by the pioneers of statistical physics laid down fundamental concepts that integrated with and preceded the formal development of information theory, showing that physical systems can indeed be viewed as computational entities that store and process information due to the dynamics of their constituent particles. The intricate workings of quantum mechanics and particle behavior reveal a deep level of complexity that is at odds with our everyday experience. For example, each atom in a balloon contains about 20 bits of information about its position and velocity with maximum precision, totaling 10 to the 25th degree of bits for all the atoms in the balloon, far more than the information stored in all the books and computers in the world. However, unlike the structured information in books, these bits are inherently random and unstructured. According to the second law of thermodynamics, the total amount of information in a system, including these seemingly random bits, never decreases. When conditions change, such as when a balloon is cooled or compressed, a decrease in the number of bits within it correlates with an increase in the number of bits in the environment, which is consistent with this law. A principle known as Landauer's principle states that information is not destroyed, but only transformed. For example, when information is removed from a computer, it is converted to thermal motion of electrons. This principle emphasizes the idea that information, visible or not, is constantly being stored and transformed. Inside a balloon filled with helium atoms, a huge amount of information is invisible to us, yet it plays a crucial role. Entropy, which is often associated with disorder, is essentially a measure of this hidden, inaccessible information. Every collision between gas atoms, far from being a simple physical interaction, is actually a computational process that performs logical operations such as and or not and copy. This conceptualization suggests that if atoms are properly arranged from the start and given the right speed, they can theoretically compute anything. However, the inherent chaotic behavior of atoms and the limitations of quantum mechanics, which makes it impossible to know precisely both the position and velocity of an atom at the same time, complicate their practical use as computational devices. Quantum mechanics introduces even more mysterious phenomena. Consider the behavior of electrons in the double-slit experiment, where electrons produce an interference pattern indicative of wave-like behavior despite being particles. This experiment shows that electrons can pass through both slits simultaneously, challenging our classical understanding of particles and demonstrating the dual partial wave nature of matter. The phenomenon of quantum superposition further complicates our understanding when particles, such as electrons, can exist in multiple states or locations simultaneously until they are measured. Decoherence theory explains why large objects, such as rocks or people, do not exhibit the same quantum behavior observed at microscopic scales. Constant environmental interaction with large objects effectively measures them by collapsing their quantum states and anchoring them to a specific location. Moreover, quantum measurement introduces singularities where the observation of a quantum state, such as the spin of a qubit, can force it into one of two states, even though it previously existed in a superposition of both. This highlights another quantum oddity, Heisenberg's uncertainty principle, which states that some properties of a particle, such as position and velocity, cannot be known exactly at the same time. In essence, the quantum world operates according to principles that defy classical intuition, representing a realm where the fundamental elements of reality behave in ways that defy our traditional understanding and perception of order and information. Can you imagine? The more information we gather about an object, the less we can know about anything else. Let's explore the most contentious aspect of quantum mechanics: measurements and the many worlds interpretation. Consider two entangled spins. If one points up, the other must point down, and vice versa. However, before measurement, they exist in an uncertain state, equally likely to be up or down. What's astonishing is that when you measure one spin on Earth, the other instantly adjusts, even if it's on the opposite side of the universe, a phenomenon Einstein humorously termed spooky action at a distance. The Einstein-Podolsky-Rosen paradox delves into this bizarre feature of quantum entanglement. suggesting a startling idea. Reality might lack fundamental elements. Imagine two coins placed in opaque boxes, one on the left and the other on the right. We know one shows heads and the other tails, but not which is which. Upon opening the left box and seeing heads, we deduce the right box must show tails. Did opening the left box influence the coin in the right box? No, it merely provided us with information about the overall system. Entangled particles behave similarly, assuring one reveals information about the other without altering it. Now, picture a particle passing through two slits, with a sensor behind one. If the particle passes through that slit, the sensor triggers. Let's introduce a cat in a box into this scenario. If the sensor triggers, the cat dies. If not, it survives. This is Schrödinger's famous cat paradox. Before measurement, the particle is simultaneously in multiple states, and the cat is both alive and dead. Some scientists propose that measurement causes the wave function to collapse, leaving only one outcome. However, quantum mechanics suggests irreversibility, challenging this view. Hence, the many worlds interpretation emerged, suggesting that with each measurement, the universe bifurcates into multiple dimensions. In one branch, the cat is alive. In another, it is dead, thus portraying reality as a multitude of parallel worlds where all potential outcomes occur. There is no agreement in the physics community about the many worlds interpretation of quantum mechanics. In 1997, I discussed this problem with Oxford physicist David Deutsch, an ardent proponent of the many worlds view. I'm not sure who came out the winner of the argument, at least in this world. Seth Lloyd. Consider a simpler perspective. Initially, the particle and the sensor exist in a superposition of two states. When the sensor is triggered, the part of the wave function, where it is silent, no longer affects future events. The two histories cease to interact. So, practically speaking, we can only consider the observed event to have happened, and the other possibilities remain unrealized. Have you ever wondered how scientists communicate with atoms? Imagine an atom as a tiny elastic ball with a nucleus made up of protons and neutrons, surrounded by electrons spinning on the outside. These electrons can occupy different energy levels or orbitals within the atom. The lowest energy orbital is called the ground state, in which the electron is most stable. However, if the atom absorbs energy, the electron can move to a higher orbital. Each atom can absorb and emit light of certain colors, corresponding to these energy level transitions. When light of the right color falls on the atom, the electron absorbs a photon and moves to a higher level. It can then emit a photon and return to its original state. This process allows atoms to communicate with us. Interestingly, during the transition from one orbital to another, the electron is in a state of superposition, simultaneously occupying both the lower and upper energy levels. In essence, the atom becomes a quantum bit, or qubit, capable of representing both 0 and 1 at the same time, much like Schrödinger's cat. When a qubit atom is asked whether it is 0 or 1, it is equally likely to answer both. By querying atoms in this way and reading their answers, we get truly random bits of information. Scientists have learned to play quantum dice with atoms by exploiting their unpredictable behavior. Of course, once measured, the state of the atom is determined, and it stops at either 0 or 1. However, there is ongoing debate about what happens to the unchosen probability, with some claiming it disappears and others suggesting it passes into a parallel reality. The atoms themselves remain a mystery. Now let's look at why quantum computers are so promising. Imagine that atoms not only store 0 and 1 like traditional bits, but also exist in superposition, simultaneously representing 0 and 1. If a classical computer is a solo instrument, a quantum computer is an entire orchestra in which the qubits act as musicians, playing their parts and blending into a harmonious melody. This parallelism allows quantum computers to perform a huge number of calculations simultaneously. It is akin to searching for a book on all library shelves at once, rather than methodically checking each one. There is one caveat, however. After measurement, atoms finally assume a single state. If we try to observe a quantum computer in the middle of a calculation, it will disintegrate into a single random result. Therefore, to get the correct result, it is best to let it compute undisturbed until the very end. Quantum computers are already gaining ground in the field of encryption. They are able to break codes that have stumped classical computers for millennia in a matter of seconds. This ability brings both hope and danger, as quantum computers excel not only in decryption, but also in search tasks. If you need to find a needle in a haystack, a classical computer sifts through the haystack one straw at a time. A quantum computer checks the entire haystack at once, greatly speeding up the search process as the amount of data increases. The most interesting application is the idea of a quantum internet. Scientists have figured out how to catch entangled photons with atoms and transmit them over long distances. You get a network of quantum computers connected by light. Seth Lloyd even dreams of creating a quantum search engine and calling it Google. Why do we need quantum computers at all? It's simple. Quantum computers have the potential to simulate the universe itself. Consider this analogy. If you wanted to recreate our world down to its atoms, molecules, and galaxies in Minecraft, a conventional computer would require an astronomical amount of time and memory. This is because everything in our universe adheres to the principles of quantum mechanics. However, a quantum computer operates under these same laws, making it perfectly suited to simulate the universe efficiently. In this simulation, each particle or atom would be represented by qubits within the quantum computer, with their interactions governed by quantum operations. The simulated model would behave identically to our real world. You could observe it scientifically and conduct experiments within it. Interestingly, the concept that our universe could function akin to a vast quantum computer isn't entirely new. Ancient Chinese philosopher Lao Tzu mused that an ideal model of the world should be indistinguishable from the world itself. And science fiction writers like Isaac Asimov have described how future humanity builds ever more powerful computers until they merge with the universe. The conventional view is that the universe is elementary particles and nothing else. That's true. But it would be equally true to say that the universe is only bits, or rather, only qubits and nothing more. The saying goes that if something walks like a duck and quacks like a duck, it is a duck. So from this minute forward, we will accept that if the universe stores and processes information like a quantum computer, and to an observer, its behavior is indistinguishable from that of a quantum computer, then the universe is indeed a quantum computer. Seth Lloyd. Some may wonder, why must our universe necessarily operate according to quantum principles? Could it not function as a classical computer or even a cellular automaton? This objection raises an intriguing question. The notion of the universe as a form of computational system was initially proposed in the 1960s by Edward Fredkin and Konrad Zuse. Konrad Zuse, an engineer, is notable for constructing the Z3, one of the first modern electronic computers, completed in 1941. Fredkin and Zuse hypothesized that the universe might resemble a classical computer or a cellular automaton, a grid of bits interacting with their neighboring bits. Their ideas were further developed by mathematician Stephen Wolfram. The idea of using cellular automata as a basis for a theory of the universe is very attractive. The problem with this approach is that cellular computers are bad at reproducing properties of quanta. For example, entanglement. Moreover, as we noted, to model a tiny quantum mechanical fragment of the universe would require a classical computer the size of the universe itself. This is why it is so hard to imagine that the universe could turn out to be a classical computer, like a cellular automaton. If it really is, then a huge part of its computational apparatus is inaccessible to observation. Seth Lloyd. Having understood quantum mechanics and quantum computing, we can now determine the processing power of any physical system with surprising ease. Imagine a perfect computer the size of a litter jar. It could perform more operations than all existing computers combined. Seth Lloyd calls it the perfect laptop. To create such a device, every particle inside it would have to be used for computing. Theoretically, this ultimate laptop could perform an astronomical number of operations per second, 10 to the 122nd degree of operations, and store an enormous amount of information, about 10 to the 92nd degree of bits. These limits are imposed by the laws of physics, which dictate how fast particles can change, state based on energy levels. If such a superpowered laptop were to operate at full power, it would generate enormous amounts of heat, reaching temperatures comparable to 1 billion degrees, akin to a nuclear explosion. Managing its heat output would require a robust cooling system to prevent meltdowns. Although our modern computers are far less powerful than this theoretical limit, their capabilities continue to increase every year, following Moore's law. According to this trend, in about 200 years, we will be able to purchase such a super powerful laptop, although technological advances may suddenly open up entirely new possibilities. Physicists are actively exploring quantum technologies that allow information to be stored at the level of individual atoms, which could lead to computers the size of a molecule, but smarter than today's supercomputers. Sounds futuristic, but the future holds many surprises. But what about the computing potential of our entire universe? Let's do the math. While the universe may be infinite in space, it has been around for about 13.8 billion years. In that time, light has traveled a finite distance, marking the observable universe, the region visible in our most powerful telescopes. Imagine that all the energy and matter in the universe is one giant computer. It stores an unfathomable amount of energy, capable of processing about 10 to the 122nd degree of operation since the Big Bang. This number is so enormous that it defies conventional labeling. In terms of storage capacity, this cosmic computer can store about 10 to the 92nd degree bits of information, far exceeding the collective computing and storage capabilities of all the computers on Earth combined. Thus, the visible universe has processed 10 to the 122nd degree of operations in its history and stored 10 to the 92nd degree bits of information, a staggering testament to the inherent computational power of the cosmos. Does that seem insignificant to you? In reality, it's more than sufficient to meticulously model everything we observe around us, every single detail, right down to the smallest particle on your fingertip. This level of computational power represents an absolute limit, beyond which no computer can exceed. But there's more. If we consider each minute event in the universe as a single operation, then our cosmos itself operates as a colossal computer. Since the beginning, moments of the Big Bang, the universe has been continually processing events, with its computational capacity growing annually as the visible universe expands and its energy resources increase. The future holds immense potential as the universe continues to accumulate computing power. What does this all imply? Simply put, viewing the universe as a quantum computer marks a paradigm shift in science. It expands traditional notions of the universe as a mere mechanism by integrating the concept of information. Energy and information emerge as the primary entities interacting to give rise to the entire spectrum of natural diversity, from basic structures to the most intricate complexities. This paradigm also suggests a path towards developing a theory of quantum gravity, aiming to unify Einstein's general theory of relativity with quantum mechanics. In this framework, each quantum computation specifies a unique configuration of spacetime. Logic elements are positioned at specific points, and the paths connecting them represent routes for quantum bits. The general theory of relativity asserts that physical laws remain invariant across different coordinate systems. Similarly, quantum computing is agnostic to its spatial and temporal embedding. What matters are the sequences of interactions among quantum bits. This perspective implies that spacetime derived from quantum computation naturally adheres to Einstein's field equations. To fully characterize spacetime in this model, we incorporate local length scales determined by the wave properties of logic elements. Their action, the more oscillations qubits undergo during computation, the more warped spacetime becomes. Information governs the geometry of the universe, and in turn, geometry influences the flow of information. This approach enables us to replicate numerous observable phenomena, from quantum fluctuations in the early universe to the dynamics of evaporating black holes. It seamlessly integrates gravitational phenomena with the behavior of elementary particles, offering a promising framework towards a theory of everything. While experimental validation of this theory remains necessary, the computational paradigm holds tremendous promise. It rests on a straightforward principle. Everything is composed of qubits. The universe functions inherently as a computational mechanism. Beginning from a simple state after the Big Bang, it has evolved into a remarkably complex entity, giving rise to galaxies, stars, planets, and eventually life itself. Scientists quantify this complexity using the concept of algorithmic information, the shortest computer program length required to reproduce a sequence of bits. In information theory, the complexity of a sequence is determined by the length of the algorithm that can generate it. Longer algorithms signify greater complexity in the sequence. Therefore, the universe's increasing complexity is explained by its computational nature, where fundamental laws of physics act as concise programs, generating immensely complex structures. Interestingly, Occam's razor, which advocates for the simplest explanations of phenomena, aligns with this concept of algorithmic information. The most plausible explanation for our orderly universe, with its intricate patterns, is that it can be generated by relatively short programs represented by the laws of physics. Random elements, such as quantum fluctuations influencing initial conditions, introduce a degree of randomness into this otherwise structured framework of the universe. Complexity itself is a multifaceted concept that scientists have long pondered. Consider the analogy of a monkey randomly typing on a computer keyboard. Most keystrokes produce gibberish, but occasionally, by chance, coherent passages or formulas emerge. Scientists sought to measure the complexity of such symbol sequences, leading to the development of algorithmic information. However, complexity is not solely determined by program length. It also factors in the computational effort needed to execute the program. Hence, logical depth emerged as a measure combining program length and operational complexity. Seeking a measure more closely tied to physical systems, scientists introduced thermodynamic depth. This measures the amount of ordered information required to construct a given system. Complex systems, like the human body, exhibit high thermodynamic depth due to their structured organization, while simpler systems formed by chance have low depth. Complexity thus represents a balance between the amount of information in a system and the effort needed to create and sustain it. Consider the analogy of mixing coffee with milk. Initially, two unmixed substances can be described by a simple program. Upon stirring, intricate patterns and swirls emerge, representing a highly complex system. Similarly, in the universe, life arises as the pinnacle of complexity, a delicate balance between order and chaos. There's another intriguing concept related to complexity: effective complexity. Imagine describing an object like an airplane. It requires detailed information about its components, shapes, materials, and more. Not all information holds equal importance. Within any system, there are ordered, regular components that define its fundamental properties, alongside random, insignificant details. Effective complexity refers to the amount of information necessary to precisely describe these structured, ordered parts of a system. For an airplane, this would encompass blueprints, wing designs, alloy compositions, and so forth. The higher the effective complexity, the more organized and structured the system appears. Living organisms exemplify high effective complexity as they require energy consumption and reproduction to sustain themselves. Consider the universe as continually engaged in quantum-level computations. Random quantum fluctuations act akin to monkeys randomly pressing keys, progressively generating more intricate structures and systems. Thus, while the universe started out remarkably simple, these ongoing computations have given rise to galaxies, stars, planets, and eventually life, with its intricate effective complexity. Looking ahead, how long can scientists envision the universe continuing its computations? What will happen to energy and information billions of years from now? A pivotal question looms. Will our distant descendants find ways to persist in existence and cognitive processes, even after stars burn out? According to current understanding, the universe will expand indefinitely. As it expands, it can accommodate more information and computations. However, the energy density necessary for these computations will diminish over time. Eventually, stars will deplete their fuel reserves. In that era, surviving descendants may harness energy by gathering matter and converting it into usable energy. Theoretical physicist Stephen Fauci from the California Institute of Technology has extensively analyzed this scenario. The maximum amount of extractable free energy can be calculated using the formula E = mc², where m represents the collected mass. Beyond this phase, gathering the scattered remnants of matter across the universe will become increasingly challenging. To sustain perpetual computing, future generations will likely adopt a strategy of slow and expand, conserving remaining energy by executing operations at progressively slower rates. This approach aims to prolong computational capabilities as energy resources dwindle. What about memory space? As the amount of available energy decreases, the memory space available in a given amount also decreases. And to keep increasing it, our immortal life form will have to spread its energy over a larger and larger volume. In other words, if you want to live forever, you have to move slowly and get fat. Seth Lloyd. One of the main challenges with the move slowly and get fat strategy is managing waste energy. Fortunately, this approach offers a solution to this issue as well. Moving at slower speeds reduces the amount of energy that needs dissipation. Additionally, being larger allows for a greater surface area to disperse this energy. However, caution is crucial. It's essential not to expand too rapidly to ensure you always remain warmer than the surrounding universe. Otherwise, the universe's radiation could engulf and potentially disrupt your system. With luck, if the universe cools down quickly enough, achieving immortality becomes a viable prospect. Suppose such a final form of life could exist. What would it look like? It would expand to encompass first stars, then galaxies, then clusters of galaxies. But in the end, it would take billions of years to think exactly one thought. Seth Lloyd. A single thought may take billions of years, but is that a big price to pay for eternity?